Welcome, everyone. This is the May Atmosphere Collaboration Team meeting. Thanks for trying out GoToMeeting. If you haven't used that before, we are using this platform so that those in NOAA and other agencies that are having restrictions on Zoom can join. A little bit of a test run. And great. Okay, so I will ask that everyone here in the meeting, instead of doing a verbal roll call, because we have 3 speakers today, to go ahead and type in the chat along with your name, which should already pop up, your affiliation, and if you have a particular interest in this meeting, let us know that. If it happens to be your first IARPC meeting, we would be interested to know that as well. So thank you. Great. And with that, Kelly, if you have any like tech advice for people, feel free to share it. If not, I'll hand it over to Barry.
Sure thing. Hi everyone, this is Kelly Ulig from IARPC. Just real quick, since this is a new platform, make sure to keep yourselves muted. You can do so by hitting the little microphone symbol on the right-hand side of your screen. It might be next to the attendees list. So yeah, Barry, over to you.
All right, well, thank you. Thank you everyone for joining us this afternoon. It is definitely starting to feel like summer here in Washington. I wanted to tell you a little bit about IARPC. It's if you click on the About IARPC, I think it show all the it's a interagency working group to coordinate all the federal research on the Arctic, and there's at least a dozen or more federal agencies that make up IARPC. The Atmospheric Collaboration Team objective is advancing processes and understanding of the changing composition and dynamics of the Arctic and the resulting changes to surface energy budgets. And so the talks today are going to be perfect for that, because we're going to be looking at both changes in atmospheric composition and dynamics. And of course, we all know if we change the ozone layer, we're changing the Earth's radiation budget, particularly letting more UV radiation to the surface. So we have 3 presenters today. We asked them each to give about a 10-minute talk. We want to make sure we have time for questions, and Ross Salowitz from the University of Maryland is going to go first.
Okay, welcome. And I indeed am going to talk about Arctic Winter of 2020. When we were preparing this, we didn't actually quite have an understanding of who our audience was. So we tried to make this, all of the talks, and mine in particular, appropriate for non-specialists. So as I look at the presenters' names, I'm a little embarrassed about this, but it is what it is. It's too late to change it. And now I'm trying to advance my screen and nothing is happening. So first off, is my title slide evident?
Yes.
Great. Yes. So the normal ways that I would advance are not, there we go.
There it goes.
Okay, and then it advanced a bunch. All right. There we go. Super. Okay, so this is a plot that we lovingly call the Newman plot. It is a plot that Paul Newman first put together. It's showing the total column ozone in the northern hemisphere in March and the southern hemisphere in October between the respective 63 to 90 degree latitude regions. We use this in the 20 questions and answers document that I led for the last update. And so Paul very kindly updated this slide to include the Antarctic winter of 2019 that I'm pointing to. Hopefully that's visible, and the most recent Arctic winter. And I just want to emphasize, I put on top here EESC, that's a metric we use. Sorry, Don and Karen, you all know this. That combines stratosphere, chlorine, and bromine into a single number. I want to emphasize that it peaked around 2001 due to the Montreal Protocol. We're only at about 11% below the peak now. So we still have lots of chlorine and bromine up there. For the most recent Arctic winter, we were about 110 Dobson units lower than we had been in 2 prior Arctic winters. And I want to also emphasize there's no scaling of the data to make the Northern Hemisphere and Southern Hemisphere match. The Northern Hemisphere ozone is always higher than that in the Southern Hemisphere. So even with the very low ozone we had this winter, averaged over the whole polar region, we're still, at a level that's much higher than the Antarctic. Okay, this is what we call a sand chart. It shows the contributions to EESC. I only want to emphasize that most of these are long-lived, and that is why we're only 11% below the peak, despite the successes of the Montreal Protocol. Now, most of you know that CFC 11 has not been going down as fast as had been expected. However, the HFCs are going down a bit faster than had been expected. So EESC is slightly up relative to where we projected it would be, but not that much different. And so this is just a way for you to see the contribution of the various species. Methylchloroform, with a much smaller lifetime than the other gases, is way down. And okay, I better move on. All right, so again, with apologies to half the people on the talk here, we care a lot about polar stratosphere clouds because they initiate this unbelievable transformation of chlorine. So once the organic chlorine gets to the stratosphere, the C is lost. We get HCl and chlorine nitrate, which are pretty unreactive. And we have all this rock and roll happening on the surface of polar stratosphere clouds, which need the air to be cold enough to form. And we get all this active chlorine and all this ozone loss. And there's so many people that worked on this. So I'm not going to cite anything other than the source of this figure, which was a chapter in a book that I wrote with 2 colleagues. All right, the chemistry that leads to polar ozone loss is very well understood. And the cycle on the top gives about 60% of the loss. This was the work of Luisa and Mario Molina, and we call this the CLO dimer. We have observations of CLO from space that are very important to us. The other set of chemistry was part of my doctoral dissertation work. I was a co-author on this paper where we pointed out bromine was also very important. Now, I want to emphasize that only about half of the BRO in the Arctic stratosphere today comes from human activities, whereas the majority of the CLO in the Arctic stratosphere today, the vast majority, but not all of it, comes from human activities. Then this chemistry is a bit complicated. We have 3 channels. I'm only showing the 2 that lead to ozone loss. The 3rd channel is actually very important. It makes a gas called OCLO, which we can observe from space. All right, moving on. This is another figure from our Arctic assessment report, ozone assessment report. Well, it might turn into an Arctic assessment report. This shows the average daily minimum temperature between these latitudes. We should use a different latitude, but now we're using 50 to 90 north. This is the Antarctic. So this is the polar cap minimum temperature, and the red is the average over all the years, and the yellow is the extrema. And this shows that usually the Arctic is much warmer than the Antarctic, and that's because Antarctica is sitting over a block of ice that kind of shields the stratosphere even from convection and planetary wave activity, whereas the Arctic is land-sea interface, lots more dynamics. All right, check this out. This is Arctic winter of 2020. We had temperatures below the threshold for PSEs out to April 6 of this year. That is insane, because the sun is fully back. I did not emphasize it, but all these ozone loss cycles need light, photons, H-nu, photons. Okay, we need light to lose ozone. We're fully illuminated with PSE conditions until April 6. And ladies and gentlemen, the world's turned upside down because in the Antarctic in 2019, we had temperatures below the PSE formation that ended prior to equinox, which is crazy. So the Antarctic usually is cold until we have full illuminated sun. Of course, we had a sudden warming in the Antarctic, but I find it fascinating that we had PSE conditions about 2.5 weeks later in the Arctic than the preceding winter in the Antarctic. And of course, everyone wants to know, are they related? And we're going to have to do a lot of research to answer that. All right, this plot shows the volume of air in the stratospheric Arctic vortex that's cold enough to have PSCs. Okay, so we calculate this as work I'm doing in collaboration with Peter van der Gothen and Marcus Rex. Yes, that Marcus Rex of Mosaic. We calculate the volume of air below PSCs. Again, very late, very unusual conditions this winter in the Arctic, and we highlighted a few other very cold Arctic winters. We have huge variability. Okay, this is a very important plot. This shows the chemical loss of column ozone in the Arctic stratosphere on the y-axis as a function of what we call the potential for formation of PSCs. This is the ratio of the integral of the volume of air in the vortex cold enough for PSCs divided by the whole vortex as units of days as we integrate a ratio dt. And the Arctic 2020 was the coldest winter in terms of this potential for formation of PSC metrics quite by far. Now, we don't find the highest ozone loss because probably we have a little bit less chlorine and bromine than we used to. For this calculation, our ozone loss is 123 Dobson units. It's based on SON measurements, some of which were launched from the Polarstern during Mosaic. So hats off to that project. And the important point of this chart is that there's a compact near linear relation between how much ozone we lose by chemistry and the potential for formation of PSCs in this metric. My last scientific slide is this one. We show a time series of PFP, the potential for formation of polar stratospheric clouds as a function of time, and it is getting monotonically higher. Our interpretation of this plot is when the vortex is stable and cold and isolated, it tends to have temperature conditions that are more conducive to formation of PSCs now than it used to in the past. We've written a lot about it. We have another paper on this that this figure will be part of that will be submitted any day now. And we're trying, of course, to understand this trend. With that, I'll put these words up that we understand the chemical mechanism. We have a relation between chemical loss and formation of PSCs. We see in the data the coldest winter is getting colder, and we do a lot of stats on it. I give you p-values. I can tell you how we do the stats, but I don't have time. I just want to throw this up here as well for the program managers. I want to emphasize, these are my thoughts, the support for the dirty work of launching radiosondes and ozone sondes is incredibly important. And I'll be happy to answer questions why. And it's very important we continue that. We can speculate about what happened this year and why it was so different. And believe me, I can speculate. But to get this to be accepted, anybody's speculation in a convincing manner is going to require years of data analysis and modeling studies to build consensus in the community. And last, but very importantly, so by no means least, spaceborne observations of these PSCs, temperature which they form, what they're composed of, what their chemical properties are, what their radiative properties are, etc. CLO and related species are so critical to testing any of these theories. And the dang-on problem is our assets are aging with no scheduled replacements. That is it for me. Okay. I actually think I've kept to 10 minutes.
Perfect, Ross. Next is going to be Paul Newman from NASA Goddard Space Flight Center, and he's going to talk about the satellite observations. Take it away, Paul.
Okay, I'm trying to share my, oh, there we go.
Do I have to do anything to unshare?
No, you're fine.
Thank you.
I just take the power away.
So good afternoon. I'm Paul Newman from the NASA Goddard Space Flight Center, and I am calling in from the home office today. So what I want to do is just show some data that was collected by the OMPS instrument, the Ozone Profiler Suite. So I'm going to show you first a couple of images. One on the left side shows March of 2019, so last year's March average. And on the right, just a single day from March of 2020, you can see this very low ozone feature sitting over the polar region. So the common situation in the Arctic is to have a mountain of ozone over the Arctic. That's the left side, and this is a very uncommon occurrence, and I'll show you how uncommon it is. So this typical March there, column greater than 400, and in March 12th, it was the average over the polar cap was 310 Dobson units. So that's a lot. Now, as I mentioned, typically we have a lot of ozone over the Arctic in March. And on the top, there's a time axis from July through June. You can see the annual cycle of ozone over the Arctic. So it's lowest, tends to be lowest in the August, September, October period, and the highest in the March and April period. In the Antarctic, because of the ozone hole, we used to have a similar situation back in the 50s and 60s where ozone would pile up over the Arctic when the polar vortex broke up. But now we have this very large depletion of ozone because of chlorine and bromine, as Ross has already shown, and we get a very low minimum of ozone over the Antarctic every year. This shows the range. These are plots that give the PDF distribution of ozone in the Arctic and Antarctic. And like the plot that Ross showed, I'll show that also. You can see that the difference between the two hemispheres. Usually you pile up a lot of ozone in March and April, and in the Antarctic, you get a lot of loss of ozone in March and April. And we understand actually why that is. It's because of poleward and downward transport of ozone into the Arctic. It tends to accumulate over the whole winter because of these atmospheric wave systems. And just to show, here's a plot of the Arctic in green. That goes along with the red curves, and you can see how low it is. That little thin red line there is actually the lowest values we've seen. So you can see that beginning in about late January, early February, we started seeing record lows of ozone over the Arctic. And that persisted all the way into April. It's heading back into climatology now, towards that thick red line that you see in the May period. Now, over Antarctic, as Ross already mentioned, there was a sudden warming in September, early September, which led to a dramatic increase of Antarctic ozone. So these are dynamical things that are driving the ozone levels. Typically, you don't have a lot of dynamics in the Antarctic in the September-October period. In ozone, the photochemistry just goes on inside the vortex. Ozone gets destroyed. You get a very deep, low ozone. Typically in the Arctic, there's a lot of dynamics, bringing in a lot of ozone. It gets warm, cuts off the depletion of ozone. Now, this is a plot of ozone over for a few different days, every separated by about 25 days, January 1st, the 26th, the 20th, March 16th, April 10th, and May 5th. And so you can see to start that there's this strong polar vortex, and it's going around. I put the streamlines on there. It goes around in a counterclockwise direction. That's what we really mean when we talk about the polar vortex. It's a huge feature of the atmosphere. It's in the stratosphere. These are powerful winds up there. And you can see on January 1st, it was pretty good. There's a lot of ozone inside the vortex. At this, it's about an altitude of about 17, 18, 19 kilometers. On January 26th, still high. By February 20th, it was going down. And then by, oops, it doesn't seem to be advancing. I don't know why. So there you can see the weak disruptions of the vortex. It's still very circular and counterclockwise. And then you can see the strong decrease of ozone mixing ratios. Now, this data is a data assimilation. It comes from the Goddard Modeling and Atmospheric Assimilation Office. And they assimilate MLS observations. So it's very close to the actual observations. And then as you get into May, all of this low ozone gets mixed over the hemisphere. So there's the low ozone getting mixed. Now I'm going to contrast two different years. I'm going to contrast 2018, which is about a normal year that we see in the Arctic, with 2020. Now in 2018, on February 20th, you see kind of a split vortex there. And by March 17th in 2018, you see a highly displaced and elongated vortex. In contrast, in February 20th and March 16th over the Arctic in 2020, you saw a pretty nice symmetric polar centered vortex. So this intact vortex with no mixing of material into the middle and no downward transport of higher ozone means that there's going to be low ozone there. Here's the plot that Ross already showed. You can see how 1997, 2011, and 2020, all very, very low total ozone years. Now, these are very reflective of a weak dynamics forcing. And now I'm going to show 8 different points, some from the 1970s and then the rest from later years. Here's 1971. This is from the BUV-4 instrument, or excuse me, the BUV instrument on board Nimbus 4 satellite, 71 and 72. And 79 is from Nimbus 7 TOMS. 1986 is also from Nimbus 7 TOMS. And then the last few years are from OMPS and the OMI instruments, 97, 2011, 2019, and 2020. So you can see how different the early years, the 1970s, are from the present. And this, as Ross already explained, this is because of chlorine and bromine. They're depleting ozone, but the other contribution is the lack of dynamics, nothing to push ozone into the Arctic region. Here's just a contrast. This is 2017 Antarctic, which would have been a normal kind of year. So you can see that a normal Antarctic ozone hole is both larger and deeper than a conventional, than a very high ozone depletion year that we see in the Arctic. So let me just summarize. March year 2020, April 2020 is likely the worst ozone depletion we've seen in the Arctic. As Ross mentioned, we'll need to do some calculations and match it up against 2011 and 1997, but it appears it's the worst we've seen. And because of the mixing of this stuff, we're going to see low ozone across the northern hemisphere because of this depletion. Now, there are other factors that influence mid-latitude ozone, but the Arctic in and of itself is lowered ozone across the northern hemisphere. Now, the reasons is the lack of planetary wave forcing from the troposphere. Amy will talk about this a little bit more, and that keeps the temperatures cold, which leads to the activation of chlorine and ozone depletion, but it also reduces the influx of ozone into the polar region. Human-produced, Ross has already explained this, human-produced CFCs and halons amplified the low ozone level by about half. So about half of the difference that we see between a normal year and this year, about half of it's due to the dynamics and half of it's due to the chemistry. If you had no dynamics, and even if there were no CFCs in the Arctic, if there's a lack of dynamics, you're going to wind up with a low of ozone over the pole in any case. Now, just a quick point about carbon dioxide. Carbon dioxide will actually cool the stratosphere and lead to a little more formation of PSCs. We think from modeling that that's not a huge, it's a good factor, but it's not a really important factor. The big factor in future Arctic levels is the increased transport of ozone that we see from aloft because of cooling by CO2. CO2 cools the upper stratosphere, slows down ozone loss, which increases ozone, and then that's carried down into the Arctic region. So CO2 in and of itself tends to increase ozone. However, and I just point that out, models show that this is the way it should happen, but there's actually not a lot of agreement amongst the models on how the polar vortex and the forcing of the polar vortex by these atmospheric waves is going to change in the future. So there's no, now just to say it, because I've been asked by a number of people and by newspaper reporters, COVID-19 has nothing to do with these ozone levels. It doesn't influence it at all. In fact, it takes, even if emissions are changed at the surface because of COVID-19, it takes about 5 years to get up over into the Arctic stratosphere. You got to carry it in the stratosphere, bring it up to the Arctic. It's just going to take a long time. So this year, nothing to do with COVID-19. And if you need more information, just go to ozonewatch.gsfc.nasa.gov, and we have lots of specific information there. So with that, thanks for your attention, and on to NOAA's Amy Butler. Thank you.
And we're really excited to have Amy. Go ahead, Amy.
Okay, 1 second. All right, can you all see my screen?
Yes, ma'am.
Yes.
Okay, great. All right, so I want to thank my collaborators on the stuff I'm going to show today, namely Zachary Lawrence, who's been leading this work, and Gloria Manny and Judith Prowitz at NOAA. Here's an image of the ozone depletion event that Paul showed. This is for a different day, March 27th, 2020, where you can see minimum ozone column values near 220 Dobson units. But around that low ozone area, there's also an area of high ozone. And the thing that's separating these two areas is the polar vortex, which is the strong winds in the stratosphere. And now I'm having some trouble getting the slides to advance, so 1 second.
You might just have to click back on the PDF.
You're right.
Welcome to the club.
Yeah, thank you. So the polar vortex, when most dynamicists talk about the polar vortex, we're referring to the winds that blow from west to east around both poles in the winter hemisphere stratosphere. And these winds are due to seasonal changes in incoming amounts of sunlight, which is absorbed by ozone. And so in the winter, when there's no sunlight coming in, the pole gets very cold, and that changes the equator to pole temperature gradient, and you get, by thermal wind gradient, a strong westerly vortex. And that happens in both hemispheres. Now, this is an image from this past winter of the Arctic polar vortex on February 16th, 2020. This is at 10 millibars. And the purple and pink just shows very strong winds occurring on that date. And now, this is a very unusual image for the Arctic. Normally, the vortex is not nearly this symmetric or as fast. This was well above average speeds for this time of year. And so we think that this was really what set up all the conditions that happened for ideal ozone depletion to occur. Normally what happens, and Paul mentioned this, but there's vertically propagating atmospheric waves from the troposphere. And in the northern hemisphere, because of land sea contrast and because of topography, these waves happen a lot more often than in the southern hemisphere. And so it causes it to weaken and warm. And usually, especially by springtime, the vortex is much too weak to be cold enough to cause ozone depletion to occur. So this gives you an idea of how strong these winds were. And the top figure here shows, as a function of latitude, the 10 millibar zonal mean zonal wind anomalies. And we have sort of a line at 60 north, which is a common metric for measuring the strength of the polar vortex. The black lines show the climatology. And what you can see is that pretty much the entire winter at 60 north, minus a small weakening in December, the vortex was stronger than normal. And by the time we got to February and March, the vortex was actually 2 standard deviations above normal. And this is during a time when normally, climatologically, the winds are decreasing in speed. The bottom plot shows the same thing except as a function of pressure instead of latitude. This is at 60 degrees north. So you can see that the event sort of started in early December in the upper stratosphere, lower mesosphere, with a very strong strengthening of the upper level jet. And following that, there was a rapid coupling from the troposphere all the way up to the mid-stratosphere of these winds that continued for the entire year from January through April. And you can see how strong those winds were throughout the depth of the atmosphere. To give you context for how this compares to past years, we can look at a time series using reanalysis data. This is using 2 reanalysis products. And so this shows the December through March average winds at 60 north. The top plot is 10 millibars, which shows that this year in 2020, the winds were record strength back to 1976, which is when the last record at 10 millibars occurred. And at 100 millibars, it was record strong throughout the entire reanalysis record back to 1958. So this is really an exceptional polar vortex. And Paul mentioned this, but when you have a strong vortex, that means it creates a very strong barrier to mixing with that ozone-rich mid-latitude air. And it also creates this region of extremely cold temperatures. So the dynamics set up this ideal ozone depletion conditions, which individual components of this have happened in other years in the Arctic. For example, we frequently have the polar vortex strengthening and intensifying, but usually happens in the middle of winter. And so it's not late enough into spring to actually do anything in terms of ozone. And so this plot shows that this year, 2020, we had the most number of days below the threshold for PSC formation, which is minus 78 degrees Celsius at 50 millibars in the November through March MERA2 record back to 1980. And the other component is that not only was it cold, but it was cold well into times when there was sunlight. So the last day on this is the bottom plot now, the last day with a vortex area greater than 10 million square kilometers in the lower stratosphere was actually early May. On average, it's closer to beginning of April. And so it really stayed strong for a long time into spring. So why did this happen? Well, we can look at metrics of vertically propagating waves. And so this is showing a December through February average of that metric over the mid-latitudes at 100 millibars, which is the lower stratosphere, and 300 millibars, which is the upper troposphere. And we can see that at 100 millibars and at 300 millibars, we're both near records for the low amount of wave propagation. So there were very few tropospheric waves making it into the stratosphere to perturb the vortex. So why is this? Well, one thing that can happen is that in the northern hemisphere, anomalous tropical convective heating can drive planetary waves that propagate into the extratropics. And if they project onto the background climatological wave pattern constructively, they can amplify into the stratosphere and break, and that weakens the vortex. But sometimes they can happen if the convection is shifted, you can actually get destructive interference, and that means that no waves can propagate up. And so something like that could be going on. We did have a very weak Central Pacific El Nino this year. There also might have been lack of Madden-Julian oscillation, convection in the right place. That can sometimes weaken the vortex. And there's also tropical stratospheric winds that drive changes in where the waves can propagate. And there were some anomalous things happening with the quasi-biennial oscillation this year. The other possibility is it's just internal variability. It could just be noise, and it could be weather, essentially. So this still needs to be figured out, and we'll need some modeling simulations to kind of get at what were the drivers of this event. So kind of summarize my last point, there really was extreme two-way coupling between the troposphere and the stratosphere. And this is a two-way interaction. So it's really hard to tell at this point whether it was the stratosphere leading the troposphere leading the stratosphere. But at any rate, it seems like simultaneously from this graph, throughout the atmosphere, from the surface all the way up to about 1 millibar and possibly even higher than that for most of the winter, there was this coupling, and here the negative or the blue colors show a very strong vortex. Now this is coupled to a pattern at the surface called the Arctic oscillation, which is a measure of mass fluctuation between polar cap and the mid-latitudes. And that time series of the AO is shown on the bottom here, and you can see that it was persistently positive for most of the winter. And so you can see that there's this coupling has an influence on surface weather. And in fact, if we look at the January through March Arctic oscillation, we see that 2020 was the most positive JFM AO index in the 70-year reanalysis record. So this goes all the way back to 1950. So really astonishingly positive AO, which indicates a polar shifted jet stream. I want to point out here that when you have a strong polar vortex, it's actually keeping the cold Arctic air trapped over the pole. And that means that mid-latitude weather will actually be anomalously warm. So when you hear about polar vortex events in the media, they're often referring to very cold weather outbreaks, but that's when the stratospheric polar vortex is broken down. It's actually weakened then. So that can be a little bit confusing, but here we can actually see the effects of that strong positive AO. So the left panel here shows January through March surface temperature anomaly for 2020. And it was a record hottest winter in many locations, particularly over Russia and Asia. And if we look at the component of that can be explained by the Arctic oscillation on the right, we can see that about 2/3 of that anomalous warmth in the mid-latitudes could be explained by this extremely positive AO event. And you can look over parts of the Arctic as well. It was actually anomalously cool over most of the Canadian Arctic and Greenland. And so this certainly had an impact on things like mosaic field campaigns that were going on up there, in addition to the fact that the AO is associated with anomalous sea ice advection, which can have an influence on what's going on up there. So it's important to be aware that this extreme event was going on when looking at the surface weather of this past winter. So the main takeaways are that a record strong polar vortex was the main driver of the conditions needed for extreme Arctic ozone depletion, but stratospheric polar vortex winds are highly variable and depend in part on weather patterns in the troposphere. And so certainly the ozone loss seen this year could happen again in coming decades if the same weather conditions, low wave forcing, set up another strong and persistent polar vortex. And finally, the atmospheric circulation, which was well coupled from the troposphere to the stratosphere, explained a large fraction of surface temperature extremes in this winter and spring 2020. I just want to end with a note that we have a special call for papers out. We have an AGU collection in JGR Atmospheres and GRL, and we're hoping anybody looking at the ozone depletion event or at transport prediction or dynamics might contribute to these this collection. And here's the paper citation for the paper we're getting ready to submit to JGR. So thank you.
Great, wonderful. Thank you so much, Amy. So we have a little bit of time for questions. Is anybody, you can unmute yourself or you can type it in the box.
Barry, this is Gijs.
Go ahead, Gijs.
Hi, thanks everyone for those really great presentations. I enjoyed them. I think many of you are aware that we're moving towards a new 5-year plan for Arctic research. And one of the things that is always good to highlight with presentations like this are kind of some of the major implications, and that helps us to kind of begin to tie pieces back together and think about how research related to these certain topics might connect to a new direction for Arctic research. So I wonder if any or all of the speakers might want to give a quick thought on kind of the major implications, and like Amy said in the end there, the special issue in fact is talking about consequences. So maybe it's good to highlight some of those consequences a little bit if possible. Thank you.
Well, hi, I'll just chime. This is Paul. I'll chime in real quick. One of the problems that we will have in the future is the aging of our satellite constellation that gives us profile information. So we'll always we have a really good trajectory for doing column observations and some ozone profiling information over the Arctic, but all of the other species we do not have replacement for. As soon as MLS and the ACE instrument on SciSat, and they're fairly old now, as soon as they go, then we're going to lose a lot of this profiling information. The other aspect to this is some of the higher Arctic stations have also had funding issues over the years, and we use those to actually monitor the situation. I mean, we can always rely on our knowledge about the meteorology, but you want to be able to actually measure polar stratospheric clouds, which is done from the Calypso instrument, but of course Calypso is aging too. So we have, right now we're kind of in a golden age of observations, and that's not going to last forever. And so there needs to be a little bit of thought about what are the primary things we need to be measuring from satellite. Thanks.
This is Ross. That's a really great answer. And so I'm not going to repeat what Paul said, but just reiterate, and this was my last slide. We really do make great use of the data from the Arctic, and it goes beyond just satellite validation. The SONs give us vertical resolution of ozone that's at a level that's greater than we can get from any other asset. So I second what Paul said. I just want to add that in terms of consequences, I mean, I'm scared by that plot of the time series of PSC formation potential just rising over time. And I think it's really incumbent on us to try to understand what's driving that. And I respectfully disagree that we can't rule out, I don't think we can rule out CO2 and the radiative forcing of climate. My group's taken a look at the CMIP6 GCMs, and we certainly see a greater tendency towards more PSCs in the future for the scenarios that run like SSP 5 8.5 than those that run SSP 2.6, and it varies monotonically with the radiative forcing and climate. Having said that, the models are all over the place in the realism of their depiction of Arctic polar vortex temperature. I think we really need to try to understand what's driving this and this rise in the propensity for PSCs at a fundamental level. And then last but not least, you know, we've identified well the failure of the Montreal Protocol CFC 11, and we could talk a lot about that. One item that we think that that's being fixed, at least in one country. We'll see whether there were other countries that are cheating in a year or two. There's another class of chemicals called very short-lived halocarbons that are used in a variety of industrial applications. They're not managed by the Montreal Protocol. They tend to have lifetimes about 6 months or so. We see that level rising in the stratosphere as well. And so, you know, we need to keep an eye on how much chlorine is entering the stratosphere, both from regulated and unregulated gases. The stratosphere has this amazing habit of redefining itself. Just when we thought the game is over and everything's understood, new issues pop up. And I think we're seeing that this winter.
But I'll add one thing, Ross. I wouldn't say the failure of the Montreal Protocol. I would say the failure of countries to enforce their own obligations.
I completely agree. I'm so sorry. If I said failure, oh yeah. I erased that. Thank you, Paul.
Okay.
I wanted to add.
Yeah, I didn't think you meant.
Go ahead, Amy.
I wanted to add that one thing that will be interesting to see is whether we have the modeling capability needed to try to attribute this event to certain forcings, or whether we're still missing correct parameterizations and capturing physical processes to be able to actually recreate this past winter. For example, there was an anomalous QBO disruption going on, and a lot of the models still aren't getting a QBO, although more of them are now. And so trying to look at that sort of thing will be really interesting.
Yeah, thanks all. That's really good kind of forward-looking insight into the things that we should be looking into over the coming decade or so. Thank you.
Jen? Oh, go ahead.
I had a question for Ross and Paul, and maybe Barry as well. Given how long it takes to get a satellite mission kind of conceived and approved and built and launched, and how concerned you are about losing the assets we have now, how much of the information that is available now from, say, MLS could be replaced with more ozone sonde locations, and how often would you have to be launching them, and how many places to understand what's going on in the Arctic stratosphere in most winters? Or would those resources be better deployed in the Antarctic, where the problem is severe, more severe?
Okay, I'll since I'm never hesitant to speak, I'll speak first. So I always get the first word, never the last word. The bane of my existence. We can replace some of the what MLS does through ground-based, like we can have ground-based measurements of CLO. They exist. Ken Juxon knows all about this program. They existed at in Antarctica for many years. It's just one place, one station. It's very intensive to maintain. Another aspect that MLS provides us that none of us have talked about is a tracer like N2O. So we look at the ozone versus N2O relation. That's vitally important for testing all of our models and all of our cockamamie ideas about what's causing ozone to change. I say that word with humor. The ozone N2O relation is very important. So if we lose satellites, we probably want to develop an N2O sonde that can go up with an ozone sonde. We could do that. But the global coverage that the satellites provide is just unprecedented. It would be a huge hit. You know, the decadal survey that I served on did rank this pretty high. And my hope is that we can get some satellite capability. I'm not advocating for any particular instrument or any species or whatever, but a rapid launch. You know, NASA's turned it around So, you know, that we have these quick turnarounds, or maybe no, I'm not even advocating for an agency, but we want to start thinking about what we're going to do, replace our aging assets on short order, I think, or we're going to just have a real information gap.
Yeah, thanks, Jack, for the question. I just reinforce what Ross said. Ozone sondes are always welcome because, as Ross pointed out, you can see structure in ozone sondes that satellites can't do. But on the other hand, there's a set of gases that just simply can't be made by balloons or ground stations. The ground stations that do measure it also suffer from the limitation of lack of vertical resolution. So sondes are really important, but like Ross already mentioned, N2O, there's the CLO that we get from, you know, some sort of set of chlorine species. So there's a few things that we just can't replace.
Maybe you guys need to get Jux to start flying the ER2 again.
Jack,
Well, ER2 is still flying.
Not in the
Just not with the instrument.
there is a IIP, so an instrument incubation program instrument that's a CubeSat version of an MLS-like instrument. So I'm hopeful that would be really nice if that instrument works, and we could get it into orbit quickly, because we know that the Aura spacecraft is going to run out of fuel in around, I think it's 2024.
Yep.
So we can still drift. Is that Ken?
Yeah, it is. In my estimation, that instrument would be, at a best case scenario, about 8 years to orbit.
Yeah, okay. All right. I was a little bit too optimistic.
Well, there's also things like, you can put together another ACE-like instrument. So there's a few options that could be done. None of them can be done because they're satellite instruments. They can't be done in a hurry.
All right. Well, this is Jack. You pointed out a very large problem for our understanding of the stratosphere, and it's something that Ken and I talk about a lot. That I wanted Jennifer Mercer just to introduce herself and give us if there's any update from the NSF side of the house.
Sure, thanks. I apologize for being late. Can you hear me okay?
Yes.
So I'm Jennifer Mercer. I'm a co-lead for the Atmosphere Collaboration Team with Barry and Heiss. And I was taking a couple of other COVID-19 related calls and had to run to this call. So when I'm not co-leading our IARPIC team, I am a program officer at NSF in Arctic Sciences and Arctic Research Support and Logistics. Were you looking for like updates from on the season and stuff, Barry, or what?
Yeah, and I was, and I was also hoping Heiss, after Jennifer's done, could give us the Mosaic update, just because it sounds like yeah.
Okay.
Sure.
So I can say that we've held a couple of office hour sessions with our program officers at NSF for the community, for any of our funded researchers or people that are developing proposals. We also help support some of the logistics in Greenland for some of the NASA projects. So I'm working closely with Torsten on those. Right now, nothing has happened in terms of research in Greenland this year, and we are anxiously awaiting Greenland to roll out their new requirements for entry, and their current requirements expire on the 1st. The plan that they're considering is going to be a 3-phase plan that we think will start at the earliest on June 15th. It will allow a limited number of people into the country per week. Those people would have to come in with a negative COVID test and then quarantine for 5 days and then be retested in Greenland. And if that test is negative, once they receive those results, then they could go about their business. So that'll help us try to figure things out for the rest of the season. We did just complete a crew change out at Summit Station. So the winter crew that was up there of 5, managing the observations, the year-round observations that occur at Summit Station, they had been there since February. We received special permission from the government of Greenland to go ahead and change that crew out, and we did so successfully finally last week with a fresh crew who had all quarantined under a very strict quarantine procedure that we developed here in the States before going up to Greenland. And they're in place now. Everybody's healthy. The outbound crew is back in the United States. They're happy to be home. And we were also able to take in additional helium during that crew change out flight for the radiosondes that are conducted twice a day in conjunction with both Mosaic and YOP. So the twice a day radiosondes at Summit will continue now, as well as the observations. And I think a bunch of the NOAA flasks came out on those flights as well. So our next mission now, our next big thing in Greenland is to look at what the rest of the season looks like beyond July, and likely that's just going to be another, although bigger effort to restaff the station, resupply the station, and then the big thing is fuel. So Summit will run out of fuel in October if we don't get fuel up there. So we're starting those conversations with the government of Greenland and the embassy and the military and everything this week, now that we've completed that mission. I don't know if Frank is on the call. If you are, Frank, you can interrupt me. Otherwise, in Alaska, there are conversations going on about Tulik, and things are changing pretty quickly, pretty often, as far as Alaska's restrictions and how they're reopening the state. Our position within NSF is that we do really want to observe the restrictions, requirements, the desires of the local community. We don't see anything as essential in terms of, life or limb type of essential. And so we encourage our research community to reach out to us, to all of our science program officers or your RSL program officers, and talk about ways to continue to make your project successful, or the original goals of your project successful, but respecting the restrictions and entry into the Arctic and stuff this year. So I can answer questions too if anybody has questions.
Great, thank you, Jen. That's some good news.
Yeah.
Hi, tell us how Mosaic is doing.
Yeah, so good afternoon, everyone. I'm Bourre. I'm also a co-lead with Jen and Barry, and I'm also a Mosaic PI, and I also have good news, which is great. So as of April, we had our last atmosphere collaboration team meeting was a meeting focused on the impacts of COVID on atmospheric research in the Arctic, and of course, Mosaic was a big topic during that conversation. Since that time, I'm happy to report that we did have a team of people first at the end of April head to Germany, undergo a 2-week quarantine period there, and every person who was there went through 3 separate COVID tests. All of them, every single one, came back negative. And so that team of people is currently on 2 separate research vessels, the Maria S. Marianne and the Sona from Germany, and they are sitting in a fjord at Svalbard, and they are waiting for Polarstern to come out of the ice to rendezvous with them there. The Polarstern is finding the passage from their ice camp to the ice edge quite challenging. The ice is fairly thick. This is, of course, one of the thicker times a year as far as the ice pack goes, and it's slow going, but they expect to be reaching Svalbard towards the end of this month, and doing a crew exchange and refueling there before heading back to the ice. Once they return back to the ice, they will initially go back to the same flow that they had been with for some time. It's looking likely that that position will eject them from the ice pack earlier than planned. And so the idea is that when the situation becomes challenging enough that they can't make the measurements they want, that they will pick everything up and then head deeper into the ice pack for the rest of the expedition. But it's very good news that they were able to work out the fairly extreme logistics associated with this new crew exchange. And so we've got a fresh team of people and fresh fuel and resupply happening right now as we speak. So everything there is going pretty well, I would say, considering all the challenges that have been faced.
All right. Well, we have about 4 minutes left. So if there's some questions anyone has, just anything related to IARPC, the Arctic.
Barry, I guess I'll just thank the speakers today. I thought it was a very great set of presentations, and I know you guys met briefly before the meeting to kind of coordinate, and I think that showed. It was a great topic to think some more about, and one that I don't often think about, but will more now looking ahead because of these presentations. So thank you all.
Yeah, this is Jen. I'd like to add my thanks to all of the speakers too. I was really looking forward to this session, and it definitely didn't disappoint. It was great, and I know it takes a lot of time, to get ready and present. So I really appreciate it. You guys were able to join us today.
3 great presentations. Amy, I really enjoyed seeing that Arctic oscillation impact, those teleconnections. The dynamics clearly played a large role. So this is good. I wish you best of luck with your publication and your special issue. It's nice not to think about COVID-19 for a few minutes. So it's a good distraction.
Yeah, thank you. We hope this special collection will be of wide interest to a number of different areas of research.
I think that this group, it's kind of scary how warm it was all through the winter in Siberia, and actually still is. And I guess they're worried about fires already starting there, and it may be another sort of air quality concern for the whole Arctic region this summer coming up.
I saw that really concern about fires. Yeah.
So thanks for the kind words, everyone. And I think that that's one of the outstanding issues is the, impact of the Arctic on surface climate. The community has certainly come to the understanding that the ozone hole has an impact on Southern Hemisphere surface climate, particularly, I believe I have this right, during summer in the Southern Hemisphere. I don't know if Amy wants to have the last word on possible impacts of the Arctic. I'm totally putting you on the spot, but if you have anything to say about possible impact of the vortex on surface climate, I'm sure our folks would love to hear about that.
Well, so clearly the strong coupling of the atmosphere from the troposphere to the stratosphere had a big impact on surface weather this winter. But I think what's particularly interesting is trying to understand how climate change influences that. And from what we found looking at CMIP6 models with sort of high vertical tops, is that there's really no consensus. Some of them show a very significant strengthening of the vortex. Some of them show a significant weakening of the vortex. And clearly, if you have a much stronger vortex, your surface temperature anomalies are going to be a lot different than if you have a much weaker vortex over time. So trying to understand why there's those differences across models, I think, is a really fascinating area of research that's still trying to be figured out.
That was excellent.
My thanks.
Yep.
I'll just say thank you also for the kind words, compliments. And I think, Amy just brought it up, the coupling between the stratosphere and the troposphere, particularly in the Arctic vortex and surface climate, are becoming is pretty well recognized now within at least the dynamical community and the forecasting community. But I think it's sort of an obligation on us on both the stratospheric dynamics and chemistry side to continue to press forward on that, particularly in a changing environment.
I also didn't really mention it, but there can be possible feedbacks between the dynamics and the chemistry. And so, a lot of the models don't have interactive chemistry right now, and there's a chance that they won't be able to capture events like this because they're not capturing the feedbacks that are going on between the chemistry and the dynamics. And so trying to understand how important it is to have interactive chemistry is another possible thing to try to understand from this event.
Barry, before we close, I just wanted to remind the group that we will meet again next month. And the current plan is to meet on the 23rd of June with a focus on the surface energy budget as observed through a variety of lenses through the Mosaic project. So we're trying to pull together teams kind of focused on that atmosphere with other parts of the Earth system in the Central Arctic Ocean.
That's a perfect way to end, Heis. Thank you so much. We're a minute over, and I appreciate everyone's spending an hour with us. Have a great rest of your week, and we look forward to seeing you next month. Thank you.
Thanks everybody.
Bye.
Thanks, everyone.